maybe let's start with chapter 11. We have the answer.
Okay.
Okay, let me share my screen. Where's the here? Start sharing. Okay. So exit out. So I think that's the chapter 11. Chapter 12. So we go. That's the chapter 11. So we good with the chapter 10, yeah?
Yeah, I think so.
Okay. So, okay, cool. Okay, so little bit muddled up. What's going on? That's chapter 11. Huh. There is something wrong with my book, looks like. Gautam, do you have 830? Oh, so there are page missing. 21, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. There is something wrong. Any of you have exercise in front of you? Mine book looks to be corrupted. Maybe if
I have a physical copy, but I don't have one.
I can open if you want. I have the.
Yeah, please go ahead. Something strange, like it doesn't. I'm gonna reopen one more time to see.
Oh, hey, Sean.
Oh, yeah, now it's fine. Okay. Oh no, hang on. Oh, strange. Something to do with my. Sometime it's coming fine. Yeah, one more time. Last time. Ah.
Does
okay.
it change when you bring it over to the main screen?
Yeah, when I go on the other screen, it changes over. So let me stop sharing and then share the small screen. Last time. Okay, so this is share. Here. Now I can see. Yeah, but when I move it, can you see the screen?
Yeah.
Okay. When I move it to a bigger screen, it just goes off. And this is the exercise. Chapter 11. Yeah. So training deep neural network. So, okay. So maybe one of you need to have answers as well. So the first question, is it okay to initialize all the weights to the same value as long as that value is selected randomly using he initialization? So what's the opinion?
No.
No, yeah. Because we don't want all of them to learn the same thing. I mean, they would all finally end up with the same values if they start with the same weights.
Correct. And I think we discussed that last time, isn't it? We discussed something similar last time. We said, okay, if we have the same value, it start going in just in a one direction. So that's why you need to have all random. Yeah.
Do you want me to read the answer or we? I can go ahead.
Any other opinion?
I think, and biases can be initialized with the same values, right? Which is 0, I think. I mean, most of the time. Not sure.
Is
It's
it
the
not
weights
one?
that have. What's that?
Oh yeah, maybe. I thought it was maybe one, like bias terms initialized to one, but maybe you're right.
Okay. Is there a reason for 1?
I don't know why I thought that.
Okay, the next question is it okay to initialize the bias term to 0? Okay.
Yeah.
Okay, maybe there's something wrong with 0. I'm not sure.
No, in the answers it says it is perfectly fine to initialize the bias terms to 0. Some people like to initialize them just like weights, and that's okay too. It does not make much difference.
Yeah.
All right.
So the bias could be zeros and ones, or any random value. It could be random values.
Seems so.
Okay. However, the other weights, the question number 1, it's better to have random values on all the weights, and then it's better if those random values are different rather than just the same value.
Yeah.
So, okay, so I understood this, but however, what difference? I think question number 1 is okay, that we don't want a network to learn the same thing, but wouldn't that hold true for a second question as well?
Sorry, what was your question, Dinesh? Can you?
The question is like why it's okay to have a same value for a bias term, while it's not okay to have same random value for the weights.
My best guess is because the symmetry has already been broken by the weights. So now, even if you start the biases with the same value, it doesn't matter. Since that symmetry is already broken, so now each node in the hidden layer has the freedom to learn different features. So it doesn't matter if the biases are same. It's when all the weights are the same, then all the nodes are basically exactly similar to each other, right? So now that we have broken that symmetry, you're free to have same initial biases because we have already broken the symmetry.
Yeah.
That makes sense?
Yes, that makes sense. But on that same assumption, would we say that the network will be more highly optimized if we have the random weights and then random biases? Or it doesn't matter because you use the term doesn't matter. So what I'm trying to gauge further is like investigate further that would the network uh, better off having a random value for both weights and the biases, or it doesn't matter for a bias as far as biases are concerned?
Yeah, there are always particular values of weights and biases that are more optimal than other values, right? So yeah, if you are able to find those optimal values, then that's always better than initializing equal values. But
Yeah, but you never know that beforehand, though, right?
Yep.
So you only know after you do some training and see if it doesn't perform well, right?
Yeah, but these things like her initialization are some, I'm not sure how exactly what method he uses, but they are certain ways of having slightly better parameters than just random, right?
Okay.
Yeah.
I don't think there's anything similar to this her initialization for biases. The biases are probably just zeros every time. Are they zeros every time?
I think they were saying that you can initialize them randomly,
No,
but
like by default in Keras or PyTorch, are the biases 0?
sure.
Yeah. So it is just common just to initialize them to 0, but it's not like necessary, right?
Yeah, not necessary.
Yeah, I see one great answer. Also I think, let me share this one here.
Initializing the biases. Yeah, I'm gonna just maybe read it loud. Initialize the biases. It is possible and common to initialize the biases to be 0. Since the asymmetry breaking is provided by the small random number in the weights, as Gautam you said, for the value in the non-linearities, some people like to use a small constant value, such as 0.01 for the all biases, because this ensures that all value units are in the beginning and therefore obtain and propagate some gradient. However, it is not clear if this provides a consistent improvement. In fact, some result seems to indicate that this performs worse, and it is more common to simply use zero bias initialization. Okay, so I guess that answered the question.
Yeah,
That
yeah.
people
The answer
have,
of Bhutan is
yeah,
okay.
people have investigated this, and then finally they come to conclusion, leave it 0 and let the network learn it. And that's looks like what is getting propagated. Okay, any more question or discussion on the question number 1 or 2, or shall we move on to next one?
Yeah, can move on.
All right, let's go. The third question: name 3 advantages of SELU activation function over ReLU. Okay, so now I need to probably bring out the SELU function first. It's been long. So let's open. Anyone want to describe how SELU is different from the ReLU? Okay.
I don't exactly know the formula for SELU, but it seems to suggest it's a scaled version of the LU.
Can someone explain what LU is?
Just trying to bring
you
it
have figure 11.3.
11.3.
So did LU come before ReLU, or
No, I think LU comes after.
okay?
I don't know, to be honest. In the book, it certainly seems to, because it's like a smoother version, right? Of like. Yeah. Well, it's more like exponent. There's no linear part to LU.
No, it's linear after in the positive side.
Oh, so it
it's
is. Yeah. Yeah.
So that's the LU.
Yeah.
So that's the LU, like it is the ReLU from here, but on the back, when it's going on a negative side, it's just going a smooth curve.
It's more like an exponential.
Yeah.
Yeah, that's the LU. That's the leaky ReLU. Go up. Okay, I think non-saturated activation function. So I'm just trying to see what is CELU then.
It doesn't give an image or a formula for cellular site.
Okay, maybe we need to look. Is the screen too small or a big for you guys?
Fine.
It's okay. It's okay.
It's okay. All right. Yeah, it's not a bigger screen. So which activation function should you use in the hidden layers? CELU, LU, leaky ReLU, and ReLU, 10x and logistic. Maybe we need to find. I remember somebody posted a very nice figure of the activation functions.
But I think in the paragraph before, right? So like, I think what that says is like, you should use CELU if you can, and if not, then you should use LU, and if you can't, then you should use leaky ReLU, like in that order. But they do say in the book that, right, the advantage is, well, it says the output, I think you might need to scroll up a little bit more to the paragraph before. Yeah. So here, there. So it says moreover, there, a paper in 2017 introduced CELU. It's a scaled variant of the LU, and then it goes on to say, if all hidden layers use CELU activation function, then this network will self-normalize. So the output of each layer already has a mean of 0 and a standard deviation of 1. And then that solves your vanishing and exploding gradients problem. But then the worst part is, like, you have to have a few conditions for that to happen, which is like the input features have to be standardized, or and you have to use a certain normal initialization, the LeCun. I guess it says that. It's just, if you scroll, that's the bullet points just beneath the paragraph.
Okay. Going up?
No, the other direction.
Other, okay. However, he never, okay, these are the things which you're saying. Yeah. Try to use a CELU in non-sequential such as a recurrent network or a network with a skip connection. Interestingly, CELU, I didn't came across CELU except in this book. And I haven't seen him using a CELU at all anywhere in chapter 12, 13, 14.
It might be because, like, in one of the bullet points, it says, that you have to use a certain normalization. Maybe everyone else is using, a certain initialization. Maybe you need to, maybe most people are using a different initialization. Maybe that's why.
Which generally people use those
yeah, so it says, like, for you to have the self-normalization, it says that every hidden layer's weights must be initialized using the LeCun initialization. So it might be why we don't see it more often, because most people are using the HE, or that initialization.
if each layer, if every hidden layer is using Lacoon normalization initialization, but in a whole initialization, we just initialize the first layer with the random initialization, or we initialize every single layer with the same initialization.
You use the same initialization scheme for every layer.
For every layer, and then perhaps, okay, that's same then.
And
yeah, but the point is like Lacoon normal initialization is different to HE initialization.
Yeah, that's correct. Yeah, and the how initialization seems to be more popular. Perhaps it's giving a more optimized results. Yeah,
I think so. The initialization that you use is, I mean, depends on what activation you use. So the reason, so I mean, for ReLU we just default to her initialization, and CellU requires Lecon initialization. But I think, like it says, the architecture must be sequential, otherwise you cannot use CellU, and the inputs must be standardized and all of that. So those might be the reasons why we don't use CellU, I guess. Because if CellU is outperforming all other activations, then people would have adopted CellU by now. There must be other reasons why we don't use CellU.
I thought it was because all layers have to be dense, because surely we standardize input anyway, right? I mean, that's very common, and most of our network is sequential. No? Like those must be features of most architecture that we use.
Is it just the input features, or the input features at all layers? I mean, like, do you get what I mean?
Yeah, I do. But I think what the CellU does is is standardized. So like once you apply the CellU, then you're in. I think so, right?
Yeah, that's what it says. Yeah.
So yeah, I think it's because like the paper only guarantees self-normalization if all layers are dense, whereas like CNNs are not dense, right?
Yeah.
Because you're not connected to.
It says sequential. CNNs are sequential, actually.
Yeah, CNNs are sequential, but they're not dense layers, or at least not.
Yeah, they're not dense.
Not every layer is dense, right?
Yep.
so that's the picture of a CellU.
It's the same. You're just, I pasted a link in the chat.
Yeah. Correct. Yeah. And he talks about the normalization here. What's the deal with the normalization? Okay, so we understood now that so it has to be two conditions. One is if you can use the CellU only when you have a sequential architecture, and then you use a Lacoon normalization rather than a Hall normalization. Okay. Be good for this question? Okay. Anybody wants to read out the answers, or do you want me to?
Can do. A few advantages of the CellU function over the ReLU function are it can take negative values, so the average output of the neurons in any given layer is typically closer to 0 than when using the ReLU activation function. And this helps alleviate the vanishing gradient problem. It always has non-zero derivative, which avoids the dying units issue that can affect ReLU. We didn't talk about any of those. When the conditions are right, i.e. if the model is sequential and the weights are initialized using liquid initialization, and the inputs are standardized, and there's no incompatible layer or regularization, such as dropout or L1 regularization, then the CellU activation function ensures the model is self-normalized, which solves the exploding/vanishing gradients problem.
Okay, cool. All right, let's move on to the next one. In which cases would you want to use each of the following activation function: CellU, leaky ReLU, and its variant, ReLU, 10H, logistic, and softmax? So in terms of the architecture, I guess. So CellU, we just said if you have a sequential architecture, then we can use a CellU. What about the rest? Any input?
So logistic is when you want to squeeze a value that ranges from minus infinity to plus infinity to a 0 to 1 range. So you want to try to predict a probability or something. And softmax is when you have many nodes in a layer and you want to make them add up to 1. So you are trying to predict among a list of labels or a list of classes.
So a logistic would be the binary, and softmax we looking for multi-class.
Yeah.
And the value is between the -1 to 1.
No, so both are 0 to 1.
Okay, so 10H would be.
Yeah, tan H is -1 to 1.
-1 to 1.
I think
So
it's used
0
in
to 1
CS.
logistic.
Yeah.
Okay. However,
ReLU is any hidden layer in between. I think leaky ReLU is also the same. So logistic would be used at the last layer, softmax as well in the last layer.
yeah. And ReLU can be in any of the hidden. How would the 10H, like from the problem perspective, would we go for like a binary or a multi-class? Would we use 10H there? Like,
No, since we want something that can represent the probability, we don't go for 10H.
yeah. So in a sense, what kind of like is it 10H fits in the end, or would it fits in a hidden layer or somewhere?
Yeah, I think it used to be used instead of ReLU. Earlier, yeah.
Okay.
It's used a lot in like an LSTM as well. Like in the LSTM cell, there's a lot of 10H. I'm not sure if you count that as an activation function. So.
Yeah, the gates and stuff, right? In the
yeah.
That's correct. Yeah. Yeah. Okay. So what about so the leaky ReLU, I think leaky ReLU sits very close to the CellU. The only difference between a CellU and leaky ReLU would be the leaky ReLU go just that curvy line, and then CellU go CellU go that curvy line, and then leaky ReLU goes straight line to the negative. So what difference in terms of like let's say in a layman terms that makes a difference? I understand you are dealing with the negative values properly, But I think, I guess if I drag that figure return, we have two here. One was, let's say this, come on. Okay, so this is the leaky one. And if I drag this guy here, that's the salute. So very small difference between the two. So this is the leaky value, which just this goes like this, and this is kind of like a curve. So the question would be, what difference in the logical term, as we were discussing, where the SLU fits, or where ReLU fits, 10H fits. So what kind of problem we're going to use either of them? I think SLU we discussed that if it's a sequential, and then if you're using Leconte normalization, use that. Or perhaps actually both the cases, both holds true for, as far as vanishing gradients are concerned, I guess. However, now the question I have is like this curve, what does this represent as compared to this direct line?
It's a good question. I'm not really sure. So maybe it is that you use leaky ReLU if you cannot use SELU or LU.
Yeah, so one, okay, logically, not mathematically, so which I see is like when you're near to zero, whatever value near to zero is, then you see the gradient is quite big here as compared to here. So you have a tiny value activation coming in. However, here you have a good activation coming when you are near to zero value. So you get good activation around here, and then you start vanishing around here. Perhaps that's what they're trying to get, that whatever activation you get around here, you get a bigger value.
So shouldn't ReLU be actually having vanishing gradient problems, since it's always zero for the negative?
Yeah, well, I think the interesting part is, that's a very good question. And then these SELUs and leaky ReLU came after ReLU. However, I guess they didn't perform as they expected, or perhaps I remember, I'm not sure if it is the figment of my imagination. This question was asked to Jeremy as well, and he said it doesn't make a huge difference. I'm not sure whether it question was asked to him or not, but this popped up in my mind as well, that okay, we moved into leaky ReLU, we moved into SELU. Why we are not using this? We're still using ReLU. They say it doesn't really much makes a huge difference, and perhaps it depends upon maybe a problem, which area or field you are working in. But it's not expert opinion. It's just my maybe somehow I read somewhere, or just my thoughts.
Yeah. Yeah, I don't know to say. Yeah, it sounds feasible, but I think I remember Jeremy saying that too, to be honest. Yeah.
So this
on searching, I can see that leaky ReLU came about because ReLU cannot have gradients on the negative side, cannot learn, and gradients cannot be back propagated. Then why don't we ever use leaky ReLU?
And yeah, and even leaky ReLU has some variants as well. It's not one leaky ReLU. I think there are some variants came in. I think this is like a parametric leaky ReLU, and I think there are a couple of more variants.
And yeah. Randomized
leaky ReLU. Yeah, exactly. There are quite a few versions of it. They didn't work. However, my question again, like going back, CellU is, what does the CellU is providing? What's not leaky ReLU providing? And here's in the mathematical terms, that's alpha bar, that's LU. This is a big investigation to go through. Okay, I don't think mathematical equation is here now. Nah, it's the LU. The only difference between this is LU, and this is like here is e raised to power x minus 1, and his e exponential of z exponential is only on a z and then minus 1. And here, oh no, this is the same. Sorry, this is the same.
It's the same except for the lambda in the front, so that's the scale.
This guy.
Mm-hmm.
Yeah, it's the same. Yeah. Okay.
Do you want me to, well, it's a very long answer, so I'm not.
Is the lambda learned in any way, or is it? Do they talk about that?
Oh, that's a good question.
Because if it's self-normalizing, then I guess something is learned or something. Or is it calculated on the spot or something? Yeah.
So let me bring it back here, lambda. Let's read this. I'll hang on a second. Let me put this in the chat here. And as for his, although it looks like a value for a value larger than 0, there is an extra parameter involved, lambda. This parameter is the reason for the S called in the CellU. When it is larger than 1, the gradient is also larger than 1, and the activation function can increase the variance. The implementation in a TensorFlow and PyTorch use the value from an original paper, which is about this. I don't think so then. It's a constant value.
Maybe like a hyperparameter.
Yeah. It is like just, I think it's just a value. It's, let's say the implementation TensorFlow PyTorch use the value from original paper, which is just 1.0507. It's similar to those, the decay value, which is kind of like same. Okay, you want to read the answers, please?
Sure, it's a long one though. So strap in. The CellU activation function is a good default. If you need the neural network to be as fast as possible, you can use one of the leaky ReLU variants instead. The simplicity of the ReLU activation function makes it many people's preferred option, despite the fact that it is generally outperformed by CellU and leaky ReLU. However, the ReLU activation function's ability to output precisely 0 can be useful in some cases. We'll see in chapter 17. Moreover, it can sometimes benefit from the optimized implementation as well as hardware acceleration. The hyperbolic tangent, tanh, can be useful in the output layer if you need to output a number between -1 and 1. But nowadays, it's not used much in hidden layers, except in recurrent networks. The logistic activation function is also useful in the output layer when you need to estimate a probability. For example, binary classification, but is rarely used in hidden layers. Finally, the softmax function is useful in the output layer to output probabilities for mutually exclusive classes, but it is rarely, if ever, used in hidden layers.
Yeah, that's correct. That's what we discussed. Okay, let's aim to get into up to at least this finish question number 7 for the next 10 minutes. Question number 5, what may happen if you set the momentum hyperparameter too close to 1 when using a SGD optimizer? Maybe it's just offshoot. Yeah, so if you put it too big a number, obviously it's going to jump over, I guess.
That's not the learning rate, right? It's the momentum.
Yeah, but then would it momentum get multiplied with the learning rate and then it's just keep moving forward?
Momentum is like how much of the past gradients are you using to calculate the, I mean, yeah. How much of the past gradients will you take into account while making the weight update, I think.
Yeah, and that is the, so okay, so that means are you using the full value of a gradient or the portion of a gradient? So that's like the momentum term to add or multiply. Yeah.
Yeah, I'll have to open the formula. It's probably something like the current gradient is yeah, I think I can see it, beta 1 m time minus 1 minus beta. Can you open that
Okay.
momentum algorithm? Yeah, m is equal to beta m minus
Yeah, I think it's equation 11.4.
11.4
on page 252. I don't know if you have the same version as I do.
How many? What page number?
352.
352. Okay.
But I'm not sure if you and I have the.
Let's try 352. Yeah, learning rate scheduling. So momentum should be somewhere here. Yeah.
It's after figure 11.5. It's equation 11.4. I know you have to go back.
Okay. Just tell me if you see 11 figure 11.5. You said.
Yeah, it's after. Yeah, right after 11.5.
Okay. 11.7.
Yeah.
11.6. Come on.
Yep, you can
Yeah,
stop here.
there.
Yeah, just this page. Yeah.
Okay. Auxiliary 3.
The next page, I think.
Momentum. Yeah. Okay.
Yes.
Let me maximize it. Yeah. So that's the momentum. Yeah.
Yes.
There's an equation a bit below. Yeah, there you go.
Is eta is momentum or beta?
Beta.
Beta is the momentum parameter. Yeah.
Yeah.
So you're using the momentum to update your weights instead of using the actual gradient.
Yeah.
As you can see in the second step. So usually theta is equal to theta minus the learning rate gradient, right? Learning rate,
Yeah.
the multiple gradient. So here instead of that, you're using m.
Yeah.
and m is basically so I think there are I have seen a different type of equation for momentum. I don't know if you guys are familiar with it. So in that one, m is basically a moving average of the gradients. So there is no learning rate that which comes in there. So m is like a moving average of the gradient, and then you update theta using that moving average. So theta is equal to theta minus or plus whatever learning rate times that moving average. So they have just slightly modified that and given it here.
So so you're saying, let's say if you take a moving average of the gradient,
Yeah,
is the momentum. Is that term get multiplied with the gradient, or would that moving average get added or subtracted from the
you use it as is
to add?
so instead of so yeah, that is slightly different from these equations which he has given here. So in your usual weight update, you have theta is equal to theta minus learning rate times gradient, right? That's your usual weight update equation. So instead of that, you have theta is equal to theta minus learning rate times the moving average of, which is basically momentum.
Yeah. So here is the answer. Simply call the momentum, which must be set between 0, high friction, and 1 is the no friction. A typical momentum value is 0.9. So it's rather close to 1. They're saying so. It's 0.90. He in a question he's asking.
So I think higher momentum means you are giving more importance to the history of the gradient rather than the current gradient, the previous gradient. Because if beta is high,
yeah,
uh,
then
okay,
there is no friction.
something is weird. There should be a 1 minus beta as well. I'm not sure why it's not there.
Okay, so he said, for example, if beta is 0.9, then the terminal velocity is equal to 10 times the gradient times the learning rate. So the momentum optimization end up going 10 times faster than the gradient descent. This allows momentum optimization to escape from plateaus much faster than the gradient descent. Yeah, but still, I think it makes sense from a momentum as a word that's going to go faster. But how? It says if you have, okay, so that's the friction he's saying. If you have higher the value, there is no friction. No friction, that means you're going to go faster. That means whatever gradients you get, you just use all of it. And then if you use the friction, let's say 0.5, so that means you're not using the whole gradient, but you using the portion of that gradient, I guess. Am I making sense?
Yeah,
I think that makes sense.
Yeah, but the important thing to remember is you're like it's the past gradients, right? It's not the current one. So beta is multiplied by m, which is the value of the previous momentum.
Okay. Yeah. Thanks for reminding me again. Yeah.
you are just ensuring that your weight update is in the direction of what gradients it has seen in the past. So the current gradient, if it slightly takes you in the wrong direction, will not be considered. You'll keep going in the direction of the previous gradients. That's what it essentially means, I think.
Okay. And you're saying that previous gradient is a
Given more
cumulative or
importance.
the
Yeah.
moving average.
Yeah.
Okay, so that makes sense actually. So as you said, then the current gradient is just one portion, but if it's a moving average of a past multiple gradients, so that means like you are going in a right direction. Even if you take a wrong step in current stage,
Yeah.
the momentum will keep you in line as
Yeah.
such. So
Yeah.
it's,
Yeah.
as you're saying, like it's the past gradient rather than a current.
Okay, yeah, it makes sense. Thank you.
Yeah.
So if you see the deep learning specialization, it has slightly different formulas, but it's essentially it might be the same thing, but yeah.
All right. Okay. Shall we do? We're just 1 minute away from 6 o'clock. Shall we do another one question, or you want to stop?
I can go.
Okay, let's do one last question. Okay. So and what we'll do is we'll reconvene back on 5 o'clock on Wednesday as well, just to complete this. So the last question is, name the 3 ways you can produce a sparse model.
What's a sparse model?
Yeah, good question.
That's a very good question.
This is not going to be a quick question.
Yeah, I totally forget to.
So I'm like, honestly, here, training a sparse model.
Okay.
So we didn't read the answer of the previous question, right?
Oh yeah.
Okay. I'm sorry. Yeah. Go ahead, Maria, please.
If you set the momentum hyperparameter too close to 1 when using an SGD optimizer, then the algorithm will likely pick up a lot of speed, hopefully moving roughly toward the global minimum, but its momentum will carry it right past the minimum.
Okay.
Then it will slow down and come back, accelerate again, overshoot again, and so on. It may oscillate this way many times before converging. So overall, it will take much longer to converge than with a smaller momentum value.
So what is the optimal value do we need to set for the momentum? Is it large or small?
I think most people use 0.9.
Yeah. So we don't use only the momentum. So we use the rate decay as well. So both go in conjunction. I think Jeremy uses both. Once you have a high momentum, low learning rate, and then I think then, or other way around, and then you switch between the two. So you have, I think, low learning rate, high momentum, and then at later stage you will have the other way around.
I think momentum is always fixed at 0.9. I think it's not changed.
Okay.
Okay.
Yeah, people don't even bother modifying it because 0.9 is like accepted as the best almost every
0.99. Okay.
No, just 0.9.
Yeah, I saw his. You see, he always shows you two figures, which is like which goes opposite to each other. One is, I think, rate decay, and one is momentum. And if momentum is going up, or maybe I'm mistaken, so I'll relook at it. In one cycle, I think he shows both of them together, and then he always say one goes up, the other goes down, and vice versa. I'll have a, yeah, I'll have a look and then come back to this. Okay, so does that answer your question, Samsudin?
Yeah, sure.
Okay, so next is sparse model. So let's do this question. Yep.
So this looks like a way to make your models small and efficient.
Yeah, that makes sense, but that is sort of like clipping. You clip, you just get rid of those small values. But then if you make the zero value for the small values, the model is sparse. But would it be going to be efficient?
Yeah, you don't have to store those weights anymore, right? So your model is much smaller now.
But you're still saving zeros instead of
No,
no.
I mean, that's the idea of sparse matrices,
Mm.
right? You are not actually storing those zeros.
Yeah. Oh, yeah. Oh, actually, yes, you're right.
So you get rid of them, right?
Yeah. I think you can actually
remove them. So you have less, in the model.
No, the architecture would be the same, but those particular connections,
okay,
they won't be active anymore.
Yeah. So
okay.
There is a way. I remember in one of the NLP class. So there is a way to store the sparse metrics as a dense values rather than storing in metrics form. It's stored into some. There is an algorithm where you just store the positional position of where the value is, and you unwrap
That's
it.
what we discussed last time.
Yeah. And then in that case, it makes sense. Then when you're storing it, you apply that algorithm, and it will store only where the values lie, and it can unpack for you when you load it.
Yeah, there is this thing like pruning of neural net. I think it's basically the same thing. So if you have weights that are really, really small, you just prune those connections off and you have a much more smaller model.
And then you call it as a sparse model?
Yeah, I've not heard of this particular term before this.
Yeah, exactly.
Apparently, yeah.
Okay, maybe Maria, you want to read the...
Sure, yeah. One way to produce a sparse model, i.e. with most weights equal to 0, is to train the model normally, then zero out tiny weights. For more sparsity, you can apply L1 regularization during training, which pushes the optimizer towards sparsity. A third option is to use TensorFlow Model Optimization Toolkit.
Okay, and that's what we discussed. All right, I think we are over in an hour, so I don't want to take more time. So maybe we can stop here. What we'll do is on Wednesday, we start from question number 7, and then try to do this practical training example. So maybe we, before we come in, and then we try it out and then come back here and have more discussion on it. What do you think? Because I think next 8th question is totally based on what you do with this. Yeah, it would be a good exercise.
Yeah, right. Yes.
Yeah.
Guys, what do you think about making the Monday session a bit longer and maybe not having a Wednesday session?
I think I'm okay, but initially we said 1 hour, and Maria, I think she can do only 1 hour, but I'll let her speak.
Yeah, I can do also 1 hour.
Oh, okay.
I can stay actually. Yeah, I reorganized my schedule so I can stay for a bit longer. I can stay definitely till 6:30.
Yeah, for me, I can stay up to 6:30, 1 hour, 30 minutes. I have to do after immediately today.
All right, good. So we will make you guys want to make it 6:30 today, or leave it to next session 6:30?
Maybe next session, I guess.
Okay. So next Monday we will do the hour and a half session there.
Okay. All right.
Okay.
And
Okay.
let's try to meet this Wednesday. Let's do 1 hour this Wednesday so that we can catch up with what we are reading.
Okay.
At
I
least
probably won't be there this Wednesday, but yeah, you guys can meet. Yeah.
Okay, so your way.
Yeah.
Okay, let's see if what about you, Maria and Shamsuddin? Would you be able to make it?
I can make it.
Yeah, I can make it
Yeah.
too.
Okay, all right. Let's do this Wednesday, and then from next week onwards, we'll do hour and a half then.
Okay.
Okay.
All right.
Cool. Thanks very much, all.
Thank you.
Thank you. Thank you.